other way. Can you, in fact, base cryptography in some sense on the hardness of MCSP? And we still don't know, but Rahul Santanam has come up with a pretty interesting and well-formulated conjecture that has as a consequence that this version of MCSP is hard on average if and only if one-way functions exist, which would go a long way toward telling us exactly where MCSP sits in the constellation of things that we care about. And this can be phrased equivalently in terms of this K capital T complexity. Okay. And a consequence of this, a consequence of his conjecture, would be ruling out the possibility that we live in a universe where everything sucks, which is called Pessyland in this framework that Russell and Pagliasso came up with. This would be a world in which there are hard problems, hard on average, but we don't get any of the benefit of that because there's also no one-way function, and so we don't have crypto. So it's sort of the worst of all possible worlds. And so this is a plausible way of getting us to believe that we really don't live in that world. Sort of related, definitely in the connection of worst case to average case reductions, we'll talk about the problem of approximating circuit size. So instead of actually, like MCSP is saying, is there a circuit of size exactly this? Now we're just asking, does this have a really small circuit or does it require really big circuits? And Hirahara, last year in an award-winning paper, showed that this approximation problem has no BPP solution, so no worst case, it's worst case hard in the probabilistic sense, if and only if this MCSP question is hard on average. And I'm lying a little bit, but not much. And you can also rephrase this in terms of K capital T complexity. And in this instance, Hirahara was also able to show that you could do this similar type of thing with the other notion of time-bounded Kolmogorov complexity, which rules out another possible universe under another plausible assumption. So the way he phrased it, it suggests that we don't live in so-called heuristica, which is the world in which P is not equal to NP, but it doesn't make any difference because everything in NP is easy on average. So MCSP has played a big role in all of these developments, but in some ways the most exciting thing, I think, deals with some other questions about approximating MCSP. Oh, I forgot about this. I'm going to skip this, even though it's some of mine. Okay. Oliveira, Pick, and Santanam studied the complexity of approximating these different notions of circuit size, or K little t or K big T complexity. And they showed that, I wonder if I sent you the wrong version of this talk. There's a more recent version of this talk that I'll be glad to share with anybody. Let me just tell you that there are a collection of lower bounds of the form. Here's a problem that requires formulae of size n cubed, Or here's something that requires branching programs of size n squared. And a lot of these things are really hard to prove. And when I would look at these papers, sometimes I would just yawn and say, why do people even bother trying to prove these things? Who cares? Because that's not going to help us answer the big questions about separating complexity classes. You know, it's not going to get us any closer to P versus NP, you know, if you're talking about things of size n cubed. But there are results showing lower bounds for MCSP that kind of match the best lower bounds on these various models that we have. And crucially, there's these exciting techniques called hardness magnification that say, if you could improve these currently existing lower bounds just a little bit, then you'd be able to answer some of your favorite questions, such as whether or not exponential time has NC1 circuits, or whether or not P is equal to NP if we're talking about slightly different variants of the problem. So for instance, Ryan and his students have looked at a version of MCSP where you're not just answering a yes or no question, but really getting your hands on the small circuit if there is one. And in the version of the talk that I had thought that I had sent, I would leave you with that inspiring thought that MCSP and these related problems that kind of sit in between the NP-complete problems and P seem to offer us a way to get around the barriers that have stood between us and exciting lower bounds, so-called natural proofs barrier and related barriers where we have a plausible strategy. It probably won't work. Nothing else has worked, but maybe we'll be wrong this time. Maybe it will actually work. You know, lower bounds that we can prove, for instance, for really simple problems like inner product mod 2. If we could prove similar lower bounds for this exponential time complete problem like computing Levin complexity, wouldn't really in that case give us P not equal to NP, but it would really break one of the log jams that we've been stuck at for a long time. And so there's exciting stuff happening, and Dymax has been a part of it. I think I've used up enough of your time.